Here we go, video number 9. Today's topic is gradients, and we'll be covering sections 410 and 411 in your textbook. 410 is arithmetic gradients, and 411 is geometric gradients. A gradient allows us to handle cash flows that change with time. So instead of perhaps a uniform cash flow, the example we saw, one of the examples we saw in the last video was a problem where we had uniform cash flows of $750 for 6 years. Well, now we can handle cash flows that change over time. So 1 year it's one value, the next year it's another value, the next year it's another value. And we will see that handling these with a spreadsheet is child's play, especially compared to what you read in the textbook. So if you look in the textbook for these two sections, in section 410 and 411, you will see a lot of formulas, and you will, the math nerds among you will want to know how you got these things and where did these complicated looking formulas come from. That would be a great discussion to have sometime, but we're not going to have it in these videos, and we're likely not going to have it in this class because solving these by hand is one thing. Using a spreadsheet makes life so much easier. As you'll see, we have a magical spreadsheet function that makes this very, very straightforward. Arithmetic gradients are gradients that change by a constant amount from 1 year to the next. For example, the first cash flow may be $200, and if the gradient is $100, it would go 200, 300, 400, 500, 600, etc. So you would continue to expand out as time went forward. You can have negative gradients, so it can be $500 to start with a negative $100 gradient. It would go 500, 400, 300, 200, 100 maybe to 0, maybe negative 100, negative 200 for however long this pattern continued. Arithmetic gradients are the initial one, section 410. After that, we'll look at an example for geometric gradients. Geometric gradients change with a constant percentage from 1 year to the next. So let's use something simple. It'll get unsimple very quickly. Let's say the first cash flow is $100 and the gradient is 10%. So in the first year it's 100, and the next year it's 110, and the next year it's 121. You get it? So it's going to increase by 10% from 1 year to the next. The next year is 10% more than the previous year. Those are the two kinds of gradients that we'll address. We'll look at two example problems to solve these. Again, I'll move a little bit more quickly with the functions, but you'll see we introduce a new function today, and this function will be the one that makes life incredibly easy for us using spreadsheets in handling gradients. Let's look at these. These spreadsheets, notice that the spreadsheet name is gradients, and once again I'll make this available as I post the video. Okay, here is the arithmetic gradient problem. The initial cash flow is at the end of year 5 is $4,500. So I'm going to put that right here, equal $4,500. And this will change. It's a positive gradient, so it will increase by $200 each year. And it says the cash flows continue until period 11. The interest rate is 7%. What is the present value at time 0? Okay, let's look at the year 6 value. It's equal to the previous year plus $200. And I'm going to use an absolute cell reference D3, so that would be $D, $3, because I want to copy this formula down, and I always want to be adding $200 to the previous year. So there's year 6, and we're going to continue until year 11. Just copy that down. And there we have the gradient series, 45, 47, 49, 51, 53, 55, 57, 100. We want to find what is the present value at time 0. So not only are we working with a gradient, we could call this a deferred gradient. That is, the cash flows don't begin immediately. The cash flows are deferred until the end of year 5. The first thing we do, just like we did in the last video, is we're going to find the present value of this series of cash flows. Now, here's the beauty. We get to use a new function, and that new function is called NPV, equal NPV, net present value. It gives us the net present value of an investment based on a series, we can continue, of cash flows, end of year cash flows for our case. Now, the beauty of this NPV function is it can handle about anything. The first argument is the interest rate, 7%. For the next argument, we're just going to put a range of values. I'm just going to highlight these values. That is the second argument of the function, and I am done. That's it. There's the answer, $27,194.78. What could be easier? So if I have a cash flow table set up like this, I can highlight the range for each, where there's a cash flow in each one of these years, I can find the present value or net present value in this case. Pretty slick. Here's one thing to know about the NPV function. First of all, it does not change the sign on your cash flows. Notice that when I entered this NPV function here, there's no negative sign in front of it. How about that? It does not change the sign on your cash flows. That's very important to remember that it doesn't. And it also still follows the same rules with relationship to P and A. That is, this P is one period prior to the first cash flow in our range. So this P is at the end of year 4. At the end of year 4. Important to remember that. Now, for some problems, you might be tempted to say, let's find a present. Is there a net future value function? And the answer is no. There is no future value equivalent to the net present value function. So if you wanted to find the future value of these cash flows, you'd need to find the present value and then move it to the future, to wherever you wanted it to go. So there's our value at the end of year 4. So the present value at time 0 requires us to take this as a future value at the end of year 4 and move it back to time 0. So this present value at time 0, I'm going to use my, I'm not going to use the present value formula, although we could. I'm going to say this is equal to my future value there. And remember, to move from a future to the present, we will divide by 1 plus I to the n, 1.07 to the 4th. There we have it. There is our net present value at time 0, the economically equivalent amount at time 0 for this series of cash flows beginning at the end of year 5 and continuing through the end of year 11. So that's it. And with gradients, with arithmetic gradients, and you'll see with geometric gradients, you know, the secret sauce is NPV. That's the function that we can pretty reliably lean on when the cash flows get a little more difficult, little uglier, non-uniform kinds of cash flows. Let me tell you one more thing here, and it's just in relation to the NPV function. Now, you might say, and let's do this, okay? We're gonna do this, and I'll show you the pitfalls. Let's take this all the way to 0. If you can find the net present value, why don't we just find the use the NPV and find the net present value all the way to 0? Let's do it. Let me look at that. NPV 7%, and instead of just highlighting the numbers we have, let's just highlight the whole thing. How about that? Start with 1 and go to the end of year 11. Now, let's see what answer we get. How about that? How about that? That's a bit of a problem. But let's see how this number changes when we put zeros in these cash flows. Son of a gun. We could have used that all the way back to time 0 and gotten the right answer. But we have to remember to put zeros in for these initial 4 years of cash flows. So it's an important thing to remember whenever you're using the NPV function for whatever sequence of cash flows you have. You need to put zeros in the periods where there is no cash flow. Just always keep that in mind. Okay, let's jump on to geometric gradients. And geometric gradients are essentially the same as arithmetic gradients, but instead of changing by a constant amount each period, it changes by a constant rate. So now we're going to increase by 4% instead of by the $200. So here we go. We begin at the end of year 5, just like the previous example, equal $4,500 for year 5. In year 6, it's going to be equal to the previous years times 1 plus 4%. Again, I'm going to make that an absolute address because I want to copy the formula down and have it always refer to the same cell. $D, $3. So the year 6 cash flow is $46.80. I can copy that down all the way down to the end of year 11. And there's our cash flows. 46.80, 48.67, on out to the end of year 11, 56.94. Again, the question that we ask here is, well, I don't ask a question, do I? What's the present value? Or we could ask, what's the future value? Let's do that. Let's answer the question. What's the future value at the end of year, let's say end of year 11? How would we solve that? Well, we'd solve it in 2 steps. Step 1, we'd find the present value, which would be the present value at the end of year 4, and we would move that forward to the end of year 11. So step 1 would be equal NPV 7% and all of the cash flows. This is at end of year 4. Remember, 1 period prior to the first cash flow. And in step 2, we'll just take that $27,075. We'll take it forward to the end of year 11. So we need to move it forward 7 years. I'm going to use my equation. It's equal to 27 times 1.07, that's 1 plus I to the 7th power, year 4 to year 11. And there we have it, $43,477.45. That's it. So arithmetic gradient, change by constant amount each period. Geometric gradient, change by a constant rate each period. And the magical NPV function that makes our life a whole lot easier. So you'll want to use that. You'll be using that NPV function a lot when you solve problems on the homework and on the quizzes coming up. So that's it. We are closing in on being finished with chapter 4. This is the foundational stuff. So everything that we've accomplished and will finish accomplishing in chapter 4 are the tools that we use then to apply to problems to start making economic decisions. So again, I encourage you to continue to work. I know some of you have been working on the extra practice problems. That's super. Continue to work on those. You also just should feel free to take problems out of the back of the chapter and be working on those. Some of the problems, some of the homework problems, I got some problem with. You know, I don't assign those on my engineering lab specifically because I've got some problems with some of them, and some of the answers that are provided I think are incorrect. So I shy away from those. But Missy and I are happy to help you answer whatever questions you might have. The more problems you work, the easier this gets. The more you use the functions, the easier it gets, the quicker you solve problems, and the easier the quiz will be. We're working on quiz 1. It's about finished. I'll post it up tomorrow. And it's a timed quiz. I'll send you more information about it, but it's going to be a timed quiz. You'll have an hour and a half to do it. And it will be much like homework problems and much like these example problems that we've presented on these videos. One other tool in my engineering lab you should find helpful is you can watch some videos of problem solutions in Excel, and that's available to you from my engineering lab. I encourage you again to view those. Sadly, you got to listen to me when you watch them, so that's not all good. But at least you don't have to look at me. You can just look at the spreadsheet and see how the problems are solved. And those problems for which it's not those problems exactly, but there are similar problems solved with the videos are indicated in the textbook with a special symbol. Okay, coming up next will be video 10, and we'll move on to the rest of chapter 4 to wipe that out. So keep working hard, and I'll be back for the next video very soon.